We saw how to use the substitution rule, the change of variable rule, U-sub, to turn harder integrals into easier integrals. But those are just for indefinite integrals. So how do we handle substitutions when we have definite integrals? Okay, there's a couple of ways to go about it, but one way is a little more direct, okay? It skips a step. I bet you'd like to know, right? Hey, let's get to it. So here's our first one here, okay? We're going to evaluate this integral from 0 to pi over 3 of sine of theta over cosine of theta d theta. Now, the clever among you may remember that sine over cosine is tangent, but we wrote it in this way to be a little more intentional, right? All right, so how do we handle this? Well, remember that we want to look for a substitution. So we want to try to find like an innermost function, or if I have a fraction, try to look whatever's in the denominator. And that's our clue. That's our clue here. Okay, remember that the derivative of cosine is minus sine. Okay, cosine's the denominator. So we're going to go ahead and make our substitution here. U is equal to cosine of theta. Okay, so du is equal to minus sine of theta d theta. And then, of course, we'll just move the minus sign over, okay, multiplied by a minus 1. But I still have these limits of integration, okay? Whoops. I still have these limits of integration, 0 to pi over 3, but that's in the theta world, okay? These are valid in theta, okay? Theta equals 0 to theta equals pi over 3. And we're going into u now. So what do I need to do? I need to get these limits of integration from the theta world into the u world, as black pen, red pen would say, okay? Theta world into the u world. We're changing units, right? These limits of integration are only valid for theta, but my new variable is u, so I want to make sure everything makes sense in u. So we're going to go ahead and take these limits of integration and plug them in, okay, into our substitution. So when u is equal to 0, okay, the cosine of theta, so the cosine of 0, sorry, when theta is equal to 0, cosine of 0 is 1, okay? And when theta equals pi over 3, the cosine of pi over 3 is, okay, think about that unit circle, use the hand trick if you know it. The cosine of pi over 3 is 1/2. And so what happens here now is that this is now going to be the integral from u equals 1/2, sorry, from u equals 1 to u equals 1/2 of, well, cosine theta is on the bottom, so we have 1 over u, okay, and d theta, sine of theta d theta is going to be minus du. Okay? This is now an easier problem. Now, you may be thinking, hey, the lower limit of integration is bigger than the one on the top. Now, we can go ahead and just keep it like this, but as you'll probably see in the homework sets, we're going to reverse the order, okay, just so that the lower limit is smaller than the top one. So we're going to go ahead and use this property here. We're going to use the fact that if I want to integrate from a to b, that's the same as integrating from b to a, but I attach a minus sign to the integral. And then, of course, okay, anytime I flip the limits of integration, it costs me a minus sign. So I can go ahead and write this integral in a more conventional manner. I have the integral from 1/2 to 1 of 1 over u du. And hey, look at that. That's easy now, right? All right. So remember, 1 over u, that antiderivative is going to be natural log of absolute u evaluated between 1 and 1/2. Now, you can go back into the original units, but that means you have to use the original limits of integration, the original variable. But why would you do that? This is just going to give you a number, okay? Remember, definite interval is the area under the curve. We get a number back. So here's what's going to happen. We're just going to go ahead and plug these numbers in. We have log of 1 minus log of 1/2. Well, log 1 is 0, okay? And log of 1/2 is, well, log of 1/2 minus log of 1/2. Or for the clever among you, okay, remember that log of 1 over x is the same as minus log of x, okay, because of exponent log rules, okay? X to the minus 1, the power gets kicked out, right? So I can also write this as just positive log 2. Okay, either one of these answers is acceptable, but that's how you handle change variables, okay? When you have limits of integration, you have to change the limits of integration as well, and then evaluate the definite integral using those new limits of integration just to make your life easier. You have fewer computations to do. Because if I went back into the original units, I'd be doing like log of, I think it's secant, or no, log of cosine of theta, excuse me. Okay, and the thing is, well, I have to find the cosine of an angle and then take the log. I don't want to deal with that. Okay, let's do this last one here. The integral from 0 to 2 of x times square root 4 minus x squared dx. Now in chapter 3, we'll learn another way to attack this integral, but here's the simple way we can do it. Look in the innermost function, okay? Inside the square root, I got 4 minus x squared, so that's going to suggest to me u equals 4 minus x squared. Get the differential. Du equals minus 2x dx. And I'll go ahead and play for the match here, okay? I have minus 1/2 du equals x dx. Okay, because I have x dx here, okay? Now, we're going to change our limits of integration. When x is equal to 0, what is u? I'm going to plug in these limits of integration to my substitution, u of 0. So 4 minus 0 squared is 4. And then when x is equal to 2, okay, plug in at 2, we get 4 minus 2 squared, which is 4. 4 minus 4 is 0. So those are my new limits of integration. So this integral now becomes, okay, the integral from 4 to 0 of x dx is now minus 1/2 du. Okay. And then square root of u. So minus 1/2 square root u du. Okay, again, if we wanted to, we can flip the limits of integration so we're in a natural order. In fact, let's just go ahead and do that. We don't have to, but we can do that if it makes us feel better. So we're going to have the integral from 0 to 4. I'll just push the 1/2 out of there, okay? Square root of u du. Okay, that minus sign, okay, comes outside as well. And then to flip the limits of integration back into a natural order, okay, I multiply by another minus. Minus times minus is plus. Now what do we do here? It's just power rule again, right? We did this a lot. Okay, so we have 1/2 times, okay, u to the 3/2 divided by 3/2, okay, because of the power rule. Add 1 to the exponent, divide by the exponent. But divided by 3/2 is the same as multiplying by 2/3. Okay, and now I'm just going to go ahead and do my evaluation step. Now, lucky for us here, when I evaluate this at 0, I'm going to get 0. That's nice, right? Okay, so we'll have, let's see, 1/2 times 2/3 times 4 to the 3 over 2. Okay, minus 2/3 times 0 to the 3 over 2. Like I said, 0 to the 3 over 2. 0 to the 3 over 2 is 0. Okay, so that term will just go away. That's good for us. Okay, 4 to the 3 over 2. I'm going to go ahead and write that off to the side here. 4 to the 3 over 2. Okay, remember that's going to be 4 cubed in a square root. Okay, but that's the square root of 4 times 4 squared. All right, because square root is multiplicative. And now what happens here, okay? Well, square root of 4 is 2. Square root of 4 squared is 4. That's just 8. So take a look at what I got here. 1/2 times 2/3 is 1/3 times 8, because 4 to the 3/2 is 8. You can check that on your calculator. So this number I get here is just 8 over 3, and that's it. So what was the extra step here? You changed variables, you change units, you change limits of integration, right? If we go from miles to kilometers, those are 1-to-1, right? 1 mile is the same as a kilometer, okay? 1 mile is 1.6 kilometers, right? So we have that scale factor. So we got to change our limits of integration when we have a definite integral. That's the one thing that we'll have to remember whenever we do definite integrals and we do a change of variable, okay? And the fun thing is, to evaluate that definite integral, you already evaluated for the easy problem, so you get the answer to the hard problem for free as well, because everything's the same. Okay, we're going to keep these principles in mind, okay? This is our first technique of integration. We're going to be using this in tandem with some of the other ones that we'll learn soon, especially in Chapter 3. Okay, we'll learn how to attack different classes of integrals, and very soon we're going to look at some applications. And I'll see you in the next one.